Okay, for people joining this live stream, we are talking about predicate logic. And the idea, well, let's take a look at example 1. Find predicate logic. Okay. Find predicate proof. Okay, so we have essentially a mortal Q. No, we're asserting Socrates is mortal.
No, it's a mortal Q. We're asking.
Okay.
Well, we're asking to prove.
Okay. So it's an interesting question how we would best represent something like Socrates is mortal. I mean, how would we naturally represent that? I mean, this is sort of a symbolic discourse language type thing because we haven't had to do things like, the predicates we've had. Well, anyway, okay, all right. But in any case, but where are these definitions? I mean, you're not. Oh, I see. These can be arbitrary. These are arbitrary definitions. Okay.
Right. They're defined by the axioms, in effect.
Okay. So for all X, all men are mortal. Socrates is a man. Now, why is that? Wait a minute. That's an assertion.
Right.
So this is a different kind of thing. So I see. So I see. I get it. I'm slowly understanding. So there's the axioms consist of a list of things that are true, which could be a for all and there implies, or it could merely be Socrates is a man. Okay.
Right. They're both valid first order logic statements.
Okay. So how would I just do the computation in our system of what's true? I mean, in other words, how would I just get the answer to Socrates is mortal here?
I mean, that's I guess the general version of that question is, given an axiom system, how do you enumerate true theorems? Right.
Well, no, it's given an axiom system. I mean, how would I resolve? Okay, in our system right now, how would I resolve? What is the function that would tell me, given this? Okay.
I guess you are thinking of full simplify or refine.
I would think so, but is that going to work with predicates like this?
They can. Sorry, I'm not sure they can handle general first order logic.
This won't work in full simplify. I'm almost certain.
Right, but so that should be possible to make that work.
Exactly. Yes, absolutely.
Okay, so this is merely the proof version of that.
Right.
What's the thing that just tries to resolve that? Refine, is that not correct?
Yes, I think so.
Okay.
But I guess refine is one of the many things that full simplify tries.
Well, I understand that, but if all I wanted to do was not simplify, but just resolve that true or false, how would I do that?
Yeah, I think it's refine, yes. Perhaps reduce. No, I think refine.
The fact that we're all confused about this isn't. Well, I don't know. That should be determined. Adam would presumably know that. But I think it's really important that we have a way to do that. So,
I mean, in effect, full simplify is already calling into the back end to find equational proof when it does equations. Right? So it wouldn't be that hard to modify it to deal with first order statements.
Fair enough. So that's a reasonable thing to do. But now my comment here, boy, I mean, okay, I'm going to make a meta comment, which is, understanding what predicate logic really is. It's so nice when there are explicit examples with just, anyway, never mind. I like this. Okay. So whatever this is, I have no idea. That's a critical pair. My God, why are there critical pairs all over the place here? Well,
but that's one of the main things we want to discuss today. The fact that even though this says find predicate proof, it is still mostly equational in behavior, and the proof is still equational. So one of the things, and I will defend it, is that this should be still find equational proof, generalized to support first order logic.
Right. This is a weird situation where it's like the theorem and the axioms are first order, but the proof, apart from some initial steps, is essentially equational.
And the initial steps are these Skolemization things or something?
Yeah, right. So this is essentially doing a simplification. There's a very common theorem prover called E, which seems to perform reasonably well in these kind of theorem proving competitions, which operates on basically the same principle, where you take the first order statement, you do Skolemization, you set it equal to a tautology in Boolean algebra, and then you do equational simplification on that. And obviously the equation will evaluate to be true if and only if the original statement was correct. And so you're just using the fast, superposition calculus that we have for equational logic to do first order logic.
Okay.
So those pink steps are where we've either sort of equationalized the first order logic statements.
Can I see that? Is this what this is doing?
Right.
So why is it? What does that mean? What is X1 here?
Okay. So equationalized axioms 4 and 5 are the equationalized forms of the two axioms you put in. So that's just a slightly modified version of the statement that you put in, and we've set it equal to this tautology, which is A or not A, in both cases.
So one of the things you're revealing here is that this is an equationalized path through doing this proof. Right. And you're saying there could be another path through doing this proof that may not be, may not involve equationalization.
Sure. Yeah. I mean, there are many ways of doing first order logic theorem proving. This just happens to be a particularly fast method.
Although it could end up being a method option for so I'm kind of agreeing with Jose here that this is because once you have a proof, let's sort of loop this back a bit. Okay. We don't have stylistic options for integrate. For instance, we could have a stylistic option. No, let me give you an example. I don't even know how you get the trigonometric solution to the cubic out of our system. Is there a way to do that? So in other words, that's a case where we could have a stylistic option. Gosh, if we don't have that, that should be in the function repository. The fact that we've gone 30 years and nobody's asked for the trigonometric solution to the cubic is an interesting sign. But anyway, it's in a sense, it's a stylistic option for what comes out. In the world of proofs, the proof is not merely, a means to an end, it is an end in itself, so to speak. And therefore it matters what comes out. And so there could be stylistic options about the proof that matter. So therefore, there's the equationalized style, and there's, even a method option. We don't really think, in most cases, a method option shouldn't really affect what comes out. It might affect, I don't know, whether the thing has this kind of cropping or that kind of cropping, but it's only a small effect. Whereas in this case of these proofs, potentially the method is everything, because it's the difference between you're going to get a trigonometric solution out and you're going to get some algebraic solution out and so on. Or am I confused?
No, that sounds completely correct.
So in a sense, by saying find equational proof, we are presetting certain expectations about the type of proof that's going to come out. There's also, all right. Well, let's look at some other examples here.
There is another argument, which is that some users have complained that they couldn't solve first order logic problems with find equational proof.
Fine. So then the argument is finished, because we should just do it that way then. They expect it. Right. We can make an argument for it. We should just do it. Okay, so what is this? There exists.
So this is a slightly more complicated example of the same thing. So before we just had universal quantifiers, this is to show that we can also eliminate existential quantifiers through Skolemization, which is a slightly more complicated procedure because you have to introduce these so-called Skolem variables to get rid of the exists.
So are you showing me what's inside the proof object, or is that hidden?
That is hidden. Sorry, I should have explained.
Is it really grotesque or not?
No, it'll look the same.
Okay, the truth is, most of these proofs are pretty useless to humans. Even the very fact that you're seeing A or not A as the version of true is just pretty human, that's pretty human hostile.
I think something like this is good to understand the method being used in simple examples like this. But yeah, for complicated cases, it's unreadable.
But, for complicated cases, we have no idea how anybody's going to use this stuff. I mean, other than I'm writing a paper, I want to, I need to show that there's a proof, print the proof in the paper. I don't know what people are going to do with this. I mean, it's really an interesting, I mean, it's very interesting to be able to say, here is a proof, and to be able to discuss some statistics of proofs and things. But when it comes to detailed reading, I mean, I guess one question is when, if we put these into Wolfram Alpha, are people going to find them useful? Elementor, have we done any of that? Have we put any proofs into Wolfram Alpha? Anybody know?
One of the summer school projects from this year will be an instance of that. Oh, the plan is to have that implemented. Remember the Boolean minimization one. Right,
but was she using the theorem prover, or was she using rules?
No, she had her own rule ontology.
Okay. Yeah, that will be a nice thing to have. But that's a show steps. That's essentially a show steps play, as opposed to a mainstream equational proof type play, which we could also have.
Right.
I mean, although it's for a different set of people, but it's still. Yeah. Okay. Well, fair enough. Let's keep going here. What is TPTP?
Thousands of problems for theorem provers. There's a big collection of these things.
Of equational equational or predicate or what?
Everything. Equational, predicate, higher order. It's sort of the standard against which theorem provers are compared. When people do these annual competitions and things, they use problems from TPTP. So I use this in particular because I wanted to compare the performance against Vampire to see how it did.
How do we do?
Ours is, it's same order of magnitude. Vampire is a bit faster, but it's not bad.
Fair enough. So if you look at that database and you look at the sort of pie chart of what's there, maybe I can even just do it.
Right.
What kinds of things are there? I mean, in other words, there's equational stuff, there's first order stuff.
Yep, there's higher order stuff, and then there's a combination. There are these relatively simple ones which tend to be kind of logic puzzly type things, and then anything that's sort of non-trivial technical math involves quite a lot of.
What are these axiom systems? That's cool.
Calculate.
This seems highly relevant to us. We should have an import mechanism that can read .ax files.
Yep, absolutely.
But this also seems relevant. I mean, I don't know what these are in terms of what order logic they are and things.
Right, but this is potentially something we could get into axiomatic theory or have axiomatic theory call into or something.
That's what I would think. I'd never run across this. Okay.
I think I mentioned it when we had an axiomatic theory meeting a while ago. I think I mentioned this, but we kind of decided that because we only supported equational logic, it wasn't worth doing. But I think as soon as we have first order, it's definitely something we should look into.
Okay. Well, what other things? Okay. Let's see. Well, he didn't spell check. Oh well. But what other things are in here? Do we know? So what does this mean? What does LCL mean? Problem domains.
This will be some branch of math. I don't know offhand what LCL is.
Let's take a look. Basic information. Well, where do they have the information on? What's the quick guide? Okay, basic test problems.
Logic calculi, it looks like.
Where?
I found there's a technical report which has all of the explanations of all the acronyms.
Well, what are they?
I mean, each one is a domain of math. LCL is logic calculator. There are Henkin models, set theory, graph theory, algebra.
This is really cool.
I agree. So anyway, yeah, examples 3, 4, and 5 are all ones that I took from TPTP.
Oh, domain structure. Okay. It's really cool. So PHI claims to be philosophy. So that would be the ones like the Socrates ones and things.
Right.
Well, we should definitely be able to
geography.
Read formats. My gosh, this is rather grotesque.
These are ontological arguments, I'd assume. Sort of Anselm type things.
Yeah, okay. So we can prove the existence or unexistence of God. My gosh. Well, we could add our solution too. All right. I mean, this seems like a really good place to. So, for example, here, what on earth would be in biology? Is that the proof of can the snail walk up the whatever based on its. There are not so many here, but. That's not very
Cell has a part.
Unlike a Euclid point. Plasmodial slime mold. No. Plasmodial slime mold is a living entity. Great. Let's look at like topology. That seems interesting. Wow. This is pretty elaborate. Okay, so this is more. So what do we think? What is this? Is this something we're going to be able to deal with, or is this some kind of higher order?
Well, the topology stuff will be higher order in general. But I mean, certainly all the first order stuff, we could in principle write a parser that just converts everything into our representation.
Okay, so if we were going to go through and make other theorem provers, what what's the next step beyond predicate? Okay, by the way, C252 from our live stream is asking, do we have materials that we could recommend for implementing a predicate logic theorem prover? Well, this is a predicate logic theorem prover, but I don't know whether people have implemented ones directly. Didn't Jan at Summer School implement one directly in Wolfram Language?
Yes. Yeah, the resolution one.
Right. So I think that's and presumably he has his project on the online.
Mm-hmm. I can post it on the live stream chat in a second, actually.
Yeah. Well, you can just pull it up just for fun. Okay. Is Jan ever going to get back to doing that temporal logic, or do we put him off horribly by the fact that the temporal logic review didn't go so well? Anyway, okay. But so if we were going to go on past sorry, if we're going to go on past past predicate logic. Well, by the way, I mean, as far as I can see, this looks just fine, what you've done here. I mean, I don't have any objection.
Okay.
I mean, these literals, yeah, I mean, I think it's fine. I mean, these are variables. For all p, those are quantified variables. These are free variables here. I mean, literals of some kind.
Mhm.
I mean, it's kind of fun that it's possible to do this. Wow. I mean, how can you conclude anything from this, though, other than what's true? I mean, in other words, what's the next thing you would like to know? I mean, other than the fact that this is a beautiful wall chart, what's the next thing? Okay, so there's two levels of hierarchy. One is the what am I saying? One is kind of what's true, and sort of the final thing is, and show me the whole proof. Okay. But the question is there an intermediate stage? Do we know any intermediate stage that's useful? I mean, there's like popular lemmas, but who cares? Those are also very machine-generated disgorgement, so to speak.
Probably the next important thing is finding counterexamples.
Okay. You mean if it isn't true, find the counterexamples?
Exactly. In fact, one could say we know that these examples are true, but we might be starting with things and we don't know whether they are true or not. And of course,
I guess sorry.
Yeah, the system will just stay there trying to prove it. So we need the opposite.
Right. So I agree. Find counterexamples would be a great function to have. I think you talked about that a bit, Jonathan, right?
I have a prototype of that, but we never got a design meeting set up.
Why isn't it basically just the same as this? Find counterexamples are just like find instances.
Yeah, so it is quite different because this is a purely syntactical thing, whereas to find a counterexample you have to construct a model. It's find equational proof find predicate proof is proof theoretic, and a find counterexample function is model theoretic. And so actually, I was going to say that the positive case of what Jose was saying is, I guess one intermediate thing you might want to say is, for a theorem that's actually true, can you find a sort of minimal model that demonstrates that it's true? So in this case,
a minimal model in which it's true, because there might be a model in which it's. I mean, if the theorem is not globally true, there might be a model for which it is true.
Right. So you can find models even in cases where the statement is independent of the axioms, because there are some in which it's true and some in which it's false.
Yeah, exactly. But so that is the analog of find counterexample, is find a model for which the thing is true, which might not tell you very much, but it at least tells you something. Okay, but why is the counterexamples case? Explain to me what is specifically problematic about having to construct the model. So in the case of equational logic, I see the model would be essentially a multiplication table for the operators. Is that
yes,
true?
Exactly. So in the find counterexample function that I made, this was probably a very far from optimal way of doing it, but essentially I just enumerated multiplication tables in which every quantified variable was assigned a number, and then every every function was converted into a function of arithmetic, and then I just enumerated such multiplication tables until eventually we found one in which the statement was falsified.
Okay. Well, it's not necessarily the case that the operators can be in terms of arithmetic, right? I mean, they just no, wait a minute. The operators are just a multiplication table. And what we're saying there is, imagine in the model that the model is simply indexed by integers.
Right, exactly.
Okay.
And so, because arithmetic is universal, so we know that eventually it will have to, if there is a counterexample, it will find it. But it may be.
What does it have to do with arithmetic? I mean, it doesn't. Why are we talking about arithmetic? I mean, it's just the multiplication table for the operator f is an arbitrary thing involving those indices, right? It just says index 7 combined with index 2 gives index 3 or something.
Mm-hmm.
So essentially, it is precisely. I mean, in like in the NKS book, we have we have examples of this there, right? So like the classic page, so to speak. Let me pull it up. I don't know if that's a good sign or a bad sign, how many times per day I actually use this thing. This picture here, right? This is showing models of certain axiom systems.
Right.
So that's another function that we need, right? Is the just generate models.
Mm-hmm.
And then you're saying one function is generate models. So what we could say, we could imagine a thing that is called find equational models of essentially axioms. And then we might have some details about the size and things like this, right? Min size, max size, max size. And then we might have, min, max. Yeah, go ahead.
Isn't the interesting case where you give not just axioms, but also a hypothesis? Because, enumerating models for axioms is just kind of trivial. What you care about in most cases is models of axioms where a particular statement is true. Don't you?
No, because you can always just add the statement to the axioms if that's what you care about.
Okay.
Okay, so this would be, this is an interesting function. So, this is basically doing this, right? I had very efficient code for getting these, by the way.
Mm-hmm.
And sometimes, you see, look at these numbers, 167772160. That's a big number. And I think I may have had, I have had good code for doing that, which we could still use. It's low-level code, but I don't see why we shouldn't use it. It's probably disembodied. It's probably a library linkable code. I bet it was a WSTP program back then. Okay, so then, so we could have find equational models. We have find counterexamples. Okay, so find instance. Right now we have find instance, which finds an instance of, in principle, find instance is doing your find a model that fits. Right? So in other words, find instance of f of a b equals f of b a. Doesn't find instance have the same idea of
But find instance doesn't allow you to define assumptions or axioms. That's the essential difference.
But it should. That third argument, which is right now a domain, should allow that. Right. So this would be find instance of f. Well, here, what we really want is we quantify over these for all AB. This thing here, find this such that axioms. That would be the form, right? That would find an instance. That would find an instance of f or multiple instances of f. So the representation of f here is as a pure function, presumably. Right, so in principle, we could solve this to get f being NAND or some such other thing. But otherwise, what f is going to be is something that says, 3, 2, 1, 5, 1, 1 or something. I think it has to be, I think it's this, right? If I'm not mistaken. I don't know if there's a better way to do it, but it's something like that. The result.
Sorry, I'm not sure the structure of the arguments is correct, because the currently defined instance takes a domain in the third argument. So this domain might be the specification of which models we are interested in.
I see, as opposed to the axioms.
Right. So perhaps we need your previous idea of having the axioms together with the.
Yeah. Okay. Fair enough. So model type basically is what you're saying here.
Right.
So this then says axioms. Yeah, it doesn't really matter what's an axiom and what's a hypothesis. Just you're trying to find things for which all those things are true.
Right. And this follows what synthetic geometry is doing in find the instance.
Ah, right. Where it says, I see, where it just has a bucket of statements, and it then says what's true. The Mathematical Musings on our live stream has a very amusing example of find an instance of an animal such that. But now I think we actually have that because we can actually do that using the entity system. Right? I mean, we can do that right now. We just say entity of, well, probably don't think we yet can do the animal subcase, but we do species. Let's do mountain such that elevation, what is it? What is the thing for a mountain? I unfortunately have to go fairly soon. Well, certainly some things like this, but greater than height of Mount Fuji. What the heck? Oh, there we go. All right. Oh, there may be a lot of them. Isn't that cool? That just worked. So it's interesting that that's a thing where our model is actually something in the real world, right? Which is very weird. I mean, that's a domain that is a real world domain. See what I'm saying? Whereas normally we are just taking idealized. By the way, I'm pointing out here that why aren't those green dots further spaced out? Why are they so clustered up?
I'm not sure. I can look into the weighting of the proof graph. I was tweaking that the other day.
Fair enough.
Oh, by the way, I just sent you. I emailed you a screenshot of a find equational counterexample, just to show you how it currently works.
My God.
So the operator is just a pure, as I say, a pure function based on arithmetic operators, and then you assign numbers to each of the.
I think the arithmetic is crazy. I don't think you should do arithmetic. I think you should just do a multiplication table. I think it's much more stable than arithmetic. I mean, yes, obviously you can represent anything. I mean, you can do, you can Gödel number it if you want to. I mean,
that's fair. It's just I don't know. A multiplication table seemed kind of unnecessarily verbose, at least in the cases I was trying. But sure.
Well, then have it be a sparse array. If the multiplication table is verbose, make it be a sparse array. I'm sure you can do that.
Okay.
Where there's a don't care thing, although there may not be a don't care. I mean, there may be a thing where the multiplication table is not fully determined, which would be interesting to know.
Right.
Okay, but I was just asking. So I really like these ideas of trying to do this. Okay, and this one we can probably make it quite efficient for the equational case.
Right.
I mean, maybe that already exists from some of the tools that we have, or maybe we can use the old code that I wrote 20 years ago or something, that I used for the Boolean algebra search. And the fact that those numbers are so huge in the NKS book does suggest that the thing was quite efficient. Okay. I'm going to have to run in a moment here. So, this looks great. I don't see problems with it. I just wanted to ask, sort of the hierarchy above the find, equational logic, predicate logic proof. What's the next stage in the sort of world of fancy theorem proving?
So systems like Isabelle, as far as I can tell, and things based on Hull, seem to have a general approach for doing, all of higher order logic, essentially. There's something called the LCF approach, which I don't completely understand. I read about it a while ago, but essentially you can. It allows for some dramatic reduction of all higher order logics into some simplified system. And so I'm not sure if we could make that work with the proof object we currently have.
So wait a minute. I know that about that stuff. The collaboration that Michael's been working on with the lean people. How is this relevant to this? Do we know?
It's still moving forward, and eventually, I think we could have another proof generator based on type theory. Yes.
I see. And so that would be a proof generator that would have the same syntax as these, or not?
Yes, same syntax, using also the same proof object, but the internals will be slightly different properties, perhaps, because we are interested in different representations. etc.
Right. Okay. I unfortunately need to run, but this is really good. I mean, I think we should just go ahead and, do the integration.
Okay.
So,
okay.
Excellent. All right.
Thanks.
See you all soon. Okay. Thanks to folks on the live stream.